defines functionality a particular type has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic type can be any type that has certain behavior. Note, traits are similar to a feature often called interfaces in other language, although with some differences. Defining a trait, a type's behavior consists of the method we can call on that type. Different types share the same behavior if we call the same methods on all of those types. Trait definitions are a way to group method signature together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple struct that holds various kinds and amounts of text, a news article struct that holds a news story field in a particular location, and a tweet that can at most 280 characters, along with metadata that indicates whether it was a new tweet, a retweet, or reply to another tweet. We want to make a media aggregator library named aggregator that can display summaries of data that might be stored in a new article or tweet instance. To do this, we need a summary from each type, and we request that summary by calling a summarize method on an instance. Listing 10-12 shows the definition of a public summary trait that expresses this behavior. Here we declare trait using the trait keyword and then the trait's name, which is summary. In this case, we have also declared the trait as pub, so that crates depending on this crate can make use of this trait too. As we can see in few example, inside the curly braces we declare the method signature that describes the behavior of the types that implement this trait, which in this case is fn summarize self string. After that method signature, instead of providing an implementation with curly brackets, we use a semicolon. Each type implementing this trait must provide its own custom behavior for body of the method. The compiler will enforce that any type that has the summary trait will have method summarize defined within. With this signature exactly, a trait can have multiple method in its body. The method signature are listed one per line and each line ends in a semicolon. Implementing a trait on a type. Now that we have defined the desired signatures of the summary traits method, we can implement it on the types in our media aggregator. Listing 10-13 shows an implementation of the summary trait on the news article struct that uses the headline, the author, and the location to create the return value of summarize. For the tweet struct, we define summarize as the username followed by the entire text of the tweet, assuming that tweet content is already limited to 280 characters. So I have defined a news article implementing summary for news article. Now I have to implement instruct implement summary for tweet. Implementing a trait on a type is similar to implementing regular method. The difference is that after IMPL we put the trait name we want to implement and then use the for keyword and then specify the name of the type we want to implement the trait for. Within the IMPL block we put the method signatures that the trait definition has defined. Instead of adding a semicolon after each signature, we use curly brackets and fill in the method body with the specific behavior that we want the methods of the trait to have for the particular type. Now that the library has implemented the summary trait on news article and tweet, users of the trait can call the trait methods on instance of news article and tweet in the same way we call regular methods. The only difference is that the user must bring the trait into scope as well as the types. Here's an example of how a binary crate could use our aggregator library crate. The code prints one new tweet, horse, e-books, of course, as you probably already know, people. Other crates that depend on the aggregator crate can also bring the summary trait into scope of to implement summary on their own types. One restriction to note is that we can implement a trait on a type only if at least one of the trait or the type is local to our crate. For example, we can implement standard library traits like display on a custom type like tweet as part of our aggregator crate functionality because the type tweet is local to our aggregator crate. We can also implement summary on vector t in our aggregator crate because the trait summary is local to our aggregator crate, but we can't implement external traits on external types. For example, we can't implement the display trait on vec t within our aggregator crate, because display and vector t are both defined in the standard library and aren't local to our aggregator crate. This restriction is part of the property called coherence, and more specifically the orphan rule, so named because the parent type is not present. This rule ensures that other people's code can't break your code and vice versa. Without the rule, two crates could implement the same trait for the same type and Rust wouldn't know which implementation to use. Default implementation: sometimes it's useful to have default behavior for some or all of the methods in a trait instead of requiring implementations for all methods on every type. Then as we implement the trait on a particular type, we can keep or override each method's default behavior. In listing 10-14, we specify a default string for the summarize method of the summary trait instead of only defining the method signature as we did in listing 10-12. Pub trait summary function summarize self to use a default implementation to summarize instance of news article. We specify an empty implementation block with implementation summary for news article. Even though we are no longer defining the summarize method on new article directly, we have provided a default implementation and specified that news article implement the summary trait. As a result, we can still call the summarize method on an instance of a news article like this. This code prints news article available, read more. Creating a default implementation doesn't require us to change anything about the implementation of summary on tweet. In listing 10-13, the reason is that the syntax for overriding a default implementation is the same as the syntax for implementing a trait method that doesn't have a default implementation. Default implementation can call other methods in the same trait even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we would define the summary trait to have the summarize author method whose implementation is required, and then define a summarize method that has a default implementation that calls the summarize author method. Pop trait summary summarize author summarize, okay, impl summary for tweet. After we define summarize author, we can call summarize on instance of the tweet struct, and the default implementation of summarize uh, will call the definition of summarize author that we have provided. Because we have implemented summarize author, the summary trait has given us the behavior of summarize method without requiring us to write any more code. This code prints one new tweet, read more from horse ebooks. Note that it isn't possible to call default implementation from overriding implementation of that same method trait as parameters. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. We will use the summary trait we implemented on the news article and tweet types in listing 10-13 to define a notify function that calls the summarize method on its item parameter, which is of some type that implements the summary trait. To do this, we use the impl trait syntax like this: puff1 notify item impl summary. Instead of concrete type for the item parameter, we specify the impl keyword and the trait name. This parameter accepts any type that implements the specified trait. In the body of notify, we can call any methods on item that come from the summary trait, such as summarize. We can call notify and pass in an instance of news article or tweet code that calls the function with any other type such as string or i32 won't compile because those type don't implement summary trait bound syntax. The impl trait syntax works for straightforward cases but is actually syntax sugar for a long form known as a trait bound. It looks like this. This longer form is equivalent to the example in the previous section but is more verbose. We place trait bounds with the declaration of the generic type parameter after colon and inside angle brackets. The impl trait syntax is convenient and makes for more concise code in simple cases, while the fuller trait bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary. Doing so with the IMPL trade syntax looks like this. Using IMPL trade is appropriate if you want this function to allow item 1 and item 2 to have different types as long as both types implement summary. If we want to force both parameters to have same type, however, we use a trade bound like this. The generic type T specified as the type of the item 1 and item 2 parameter constrains the function such that the concrete type of the value passed as an argument for item 1 and item 2 must be the same. Specifying multiple trade bounds with the plus syntax, we can also specify more than one trade bound. Say we wanted notify to use display formatting as well as summarize on item, we specify in the notify definition that item must implement both display and summary. We can do so using the plus syntax. The plus syntax is also valid with trade bounds on generic types. With two trade bounds specified, the body of notify can call summarize and use uh, curly braces to format item. Clearer trade bounds with where clauses. Using too many trade bounds has its downside. Each generic has its own trade bounds, so function with multiple generic type parameters can contain lots of trade bound information between the function name and its parameter list, making the function signature harder to read. For this reason, Rust has alternate syntax for specifying trade bounds inside a where clause after the function signature. So instead of writing, we can use a where clause like this. Okay. This function signature is less cluttered. The function name, parameter list, and return type are close together, similar to a function without lots of trade bounds. Returning type that implements trade. We can also use the IMPL trade syntax in the return position to return a value of some type that implements a trade, as shown here. By using the IMPL summary for the return type, we specify that the returns summarizable function returns some type that implements the summary trade without naming the concrete type. In this case, returns summarizable returns a tweet, but the code calling this function doesn't need to know that. The ability to specify return type only by the trade it implements is especially useful in the context of closures and iterators, which we cover in chapter 13. Closures and iterators create types that only the compiler knows or types that are very long to specify. The IMPL trade syntax lets you concisely specify that a function returns some type that implements the iterator trade without needing to write a very long type. However, you can use IMPL trade if you are returning a single type. For example, this code would return either a news article or a tweet with the return type specified as IMPL summary wouldn't work. Returning either a news article or a tweet isn't allowed due to restriction around how the IMPL trade syntax is implemented in the compiler. We will cover how to write a function with this behavior using trade objects that allow for values of different type. Using trade bounds to conditionally implement method. By using a trade bound with an IMPL block that uses generic type parameters, we can implement method conditionally for types that implement the specific traits. For example, the type pair in listing 10-15 always implements the new function to return a new instance of pair. Recall from the defining methods section of chapter 5 that self is a type alias for type of the IMPL block, which in this case is pair. But in the next IMPL block, pair only implements the CMP display method of if its inner type to implements the partial order trade that enables comparison and the display trade that enables printing. We can also conditionally implement a trade for any type that implements another trade. Implementation of a trade on any type that satisfies the trade bounds are called blanket implementation and are extensively used in the Rust library. For example, the standard library implements the toString trade on any type that implements the display trade. The IMPL block in the standard library looks similar to this code. Because the standard library has this blanket implementation, we can call the toString method defined by the toString trade on any type that implements the display trade. For example, we can turn integers into their corresponding string values like this because integers implement display. Blanket implementations appear in the documentation for the trait. In the implementers section, trait and trait bounds let us write code that uses generic type parameter to reduce duplication, but also specify to the compiler that we want the generic type to have particular behavior. The compiler can then use the trait bound information to check that all the concrete types used within our code provide the correct behavior. In dynamically typed languages, we would get an error at runtime if we call a method on a type which didn't define the method, but Rust moves this error to compile time, so we are forced to fix the problem before our code is even able to run. Additionally, we don't have to write code that checks for behavior at runtime because we have already checked at compile time. Doing so improves performance without having to give up the flexibility of generics. So we will check validating references with lifetime in next video. Thank you for watching.